First, I will present briefly a project that was quite fascinating, and I brought two of my graduate students with me, that Eric and Alec, who really did make it happen with the rest of the team. This was a project and where we involved several students, several groups. The important issue is that in aerospace engineering, in aviation, there are so many important issues like fuel savings and also noise reduction that is necessary. We discussed these issues at the CDIO meeting some time ago at Duke University, where Boeing talked about following the in designing processes, but they never followed upon that decision. So I went ahead and contacted some Boeing engineers in the Phantom Works that they should be considering a project with several teams. So NASA is also on board with the environmentally responsible aviation program that they have. And that was basically the starting of the project. The main vehicle that NASA is promoting for environmentally friendly is the X-28, where you see a picture there, was our basic design where we started from. And a few ideas that we have: the goals: reduce fuel consumption, reduce emissions, and reduce noise, all at the same time. The number of passengers going in the air will double the next few years, so we have a huge problem in terms of fuel consumption, noise at the airports, and so on and so forth. And then an example here is a typical airport boundary. Today, the footprint of aircraft is like this, the noise footprint is like this. The goal is to reduce that noise footprint to this level so that it's almost inside the aircraft, the airport boundaries. So we have to develop those kind of technologies. And also in terms of fuel consumption, numbers are staggering. What is produced or used as fuels, for example, and also production of CO2 and NOx in this thing. And again, NASA has a goal to reduce the fuel burn by 50% in 2020 and even 70% beyond that. So the blended wing body vehicle is known as a very aerodynamically efficient vehicle. So we took that as a baseline for the project. And then after that, I wanted to have the global component in it. So I contacted colleagues in Stuttgart, Germany, and colleagues in Sydney, Australia, to have a group of students at each of these schools work together on this project. And that led to a charter to the team to basically CDIO an aerial vehicle to investigate new technologies for improvements and capabilities and efficiency for aircraft, and practice international cooperation on this project. In addition, I had an undergraduate team also participating. So the undergraduate team was let's say, the specialist in propulsion technology for this vehicle. We ended up with a nice team from all the schools around the world, and we have now the vehicle ready, and Eric will talk a little bit about the concept.
Thank you, Jean. I'm Eric Serrani. I was the lead configuration manager on this project, and I'll be going over exactly what we created and how we went through the process of working with a few other schools on this. So up there you see our final aircraft. It's the Hyperion. It's a 3-meter wingspan flying wing design. We designed it to be a tractor propeller configuration, and it's actually axis stable so that we could fly it off of basic RC control. We did eventually design a control system around it, but we wanted it to be stable so that it could be flown without that. The aircraft was designed completely out of composite material just to keep the weight down, and then we also adapted a hybrid electric engine that John was talking about before, that's licensed by the company Tygon Intertech at the University of Colorado. Now, the 3 schools that were working on this had different responsibilities. The University of Colorado, we were in charge of the management of the program. systems engineering, we also did the internal structure and design. University of Sydney worked on the preliminary aerodynamics. Germany did CFD, wing designs, and some other analysis. You can see the graphical representation up there. CU is kind of all-encompassing on the project, managing these other 3 teams that were involved, the propulsion system, and the aerodynamics as well from the other schools. This is a sample of the concept of operations of the vehicle. It really drove the design of the hybrid engine, and what we wanted to do was highlight the different modes of operations of the hybrid engine and the capabilities that it provided. So on takeoff, it would use blended power from both an internal combustion engine and an electric motor just to get that extra boost on takeoff. During the cruise portion, it's much more efficient to burn gas rather than batteries, as the energy density of gas much higher than what you get out of batteries. We wanted to provide a dash mode in which you can use full power from both engines at the same time in case you needed it out of a situation. And then most importantly, for the noise aspect, we wanted to demonstrate the quiet mode, shutting off the internal combustion engine with just the electric engine only, and then again landing in electric only to demonstrate reducing airport noise. Now, some of you may have been at the conference last year where a team named Helios presented the hybrid electric engine. This was a first iteration of it. We created another undergraduate team, Solstice, to improve upon this engine. We went from a offset drive where the ACE and the EM are offset from each other, coaxial drive. The Helios had no control system on it. It was controlled by 2 different rather than a single stick, and was driven by efficiency. And whereas this project had multiple flight modes, a control system, and was driven by reliability and operations. So I'll go through a few of the design teams that we had. Aerodynamics and Structures were 2 different teams, and they work closely together. Some of the requirements is to have a lift-to-drag ratio of greater than 20 and to be so that we could fly. Down in the picture on the bottom left, you can see a few of the design iterations that were thrown back and forth between the schools. The 2 blue models are from the University of Sydney. The black and yellow models are from the University of Colorado. And each time we would take a design and further improve upon it, and we kind of blended the ideas together until we came up with what you see in the top right there. This design, we were continuously improving it. However, it needed be locked down early on, even though more ideas were coming up on how to improve it. And this was locked down so that we can complete the rest of the design of the airplane, like the internal structure and the electronic control system. The University of Germany did great work on designing some extremely efficient wing endings and vertical tails, and did some analysis on this as well. Now, this diagram shows exactly how the manufacturing occurred during the 2nd semester. This all occurred very quickly and in parallel. So in the United States, we built the internal structure, put everything together, and then we had to ship that internal structure over to Germany, integrated it with the center body. They were center body skin they made there. Simultaneously, while they're integrating the center body, we were designing the wings and manufacturing the wings. They shipped the center body to us, to the United States. We integrated the wings, and at the same time, the University of Sydney in Australia made a half-scale wind tunnel model, did aerodynamic validation, and compared it to CFD validation that was done in Germany. So altogether, we were working in collaboration in an extremely short period of time, but having 3 different universities allowed us to do this. And this is a very complicated electronic system that required a lot of systems engineering, being able to know what systems were talking to each other and the needs of the pilot were. We had a ground station that had to receive information from a data acquisition system that was both downlinking telemetry in real time and recording it on board, as well as providing a first-person vision to the pilot in case that he needed to see it. However, our pilot was very skilled in RC training and didn't even need to look at the first person. In addition, we had a flight control system that used some sensors in 6-axis IMU to provide stability to the aircraft, even though it was statically stable in 3 axes. As far as testing goes, it was really helpful to have the global collaboration in this. As we found out through about 20 crashes of our prototypes, there was a CG problem. We couldn't figure out why through our analysis that we did before. One of the students at the University of Sydney did some investigation on the prop wash, and it actually moves the dynamic center of the aircraft forward, and thus we had to redesign, put the CG a little bit more forward. University of Stuttgart validated this with their CFD results. We made the changes, and we finally got a flying aircraft that flew beautifully. And now I'll hand it over to Alec to talk about the international collaboration some more.
Thank you, Eric. So my name is Alec Velasco. I was the project manager for this entire project, and it was quite the experience, I can tell you. But what I talk about here is the follow the sun idea. You know, having 3 universities around the globe, you know, we had some advantages that we were able to employ. Having each team was apart, one team could work, hand it off to the next team when they were done with the day, who would then hand it off to the next subsequent team, and it would basically circle our design development every day. We basically employed it at different levels and stages, and I'll explain that in a second. But the main advantage was really it allowed us to do a quick conceive phase of the design project. We were able to get a lot of our stuff much more quickly and rapidly than we if we were just a single team. But moving into doing CATIA and SolidWorks modeling, it allowed us to have staged of what needs to be done each week, each day, and each individual team member around the globe was able to work together and basically produce the aircraft. Here's kind of an example of what was a typical day like. At University of Colorado, we would have a structural requirement or a structural design that we were working on. We changed the wing spar thickness. Well, then we'd have to ask ourselves, how does that impact our requirements? How does that impact the aerodynamics, the rest of the vehicle? Then at the end of that day, we'd have these questions. We could hand them off to our Sydney team. And Sydney would, we're working on the aerodynamics, so would say, okay, how does changing our thickness affect if we, increase the size of our aerodynamic thickness of the wing? They would work on, come up with their evaluation, come up with their designs, send that to Germany. Germany would then look at how would the structure change based on this. And everyone, kind of cycled on a given day. And the next day when I came to school and to work, essentially, we had a much better understanding of where we were, where we needed to be, and could move forward. Working in an international team and doing a full project from start to finish, including manufacturing, there's a lot of risk involved. We had to come up with a lot of different ways to mitigate those risks. For example, during the second semester, we had to integrate the electronics in the center body of the aircraft. Well, at that point in time, the center body of the aircraft was already manufactured by us and sent to Germany, so we didn't have the mock-up there. So we took ideas from other aerospace industries, such as a satellite industry, where they use what they call a flat sat. Flat sat's a CubeSat, where they flatten it out and can do all the internal layouts and components, make sure everything fits. We took the same idea and integrated it into the aircraft and basically built our own flat sat mock-up while the center body was in Germany. We made our own version relatively quickly, cheaply, and we're able to do all the integration work that we needed to do, and it proved to be very successful. As far as the manufacturing of the actual airplane itself, we worked on, as I said, the internal structure. We shipped that to Germany. They put the center body to it. And then we also, while they were putting the center body on the internal structure, we made the wings. Well, we didn't want to have the airplane come back to the University of Colorado and things not match. So we came up with an dimension template, which is this acrylic laser cut template that you see here. And what we did was, at the very beginning, when we sent things to be manufactured in different countries, we made all of the individual interface templates at the University of Colorado. We knew they matched. We knew the specifications. We knew if we made our wings to that piece and they built the center body to that piece, there would be no problems when they came back, and it proved very successful. We also did similar things like this throughout the entire design process, and it was very valuable for everyone. I'll speed up a little bit. Here, quickly, there's a schedule overview. The only things I really want to highlight are, we have the start phase, the PDR, that's to conceive. PDR to CDR is really design phase of the project. After the CDR milestone, which is very important to make sure that we remained on schedule, we go to the second semester where we flight testing and the implementation of everything. It's extremely fast-paced, however, it can be done. It's important to note that each university had a different schedule. They all started semesters at different times. We started in the University of Colorado second, so I actually started a month early to work with the University of Sydney, and we ended up bridging the gap in the Sydney semester. Some very motivated students to work over their summer. Here's just a quick overview. Again, we had design phase in the middle in the blue, software is in the light blue, and that's a little different because software is kind of always designed. It takes a second to run a computer. And then manufacturing testing in the second semester was really when we get to implement and operate our vehicle. Best practices, there's a lot of tools out there. Skype, internet is fantastic. We were able to really communicate well with all of our teams. Using system engineering really taught us where to go, where to start from, how do we end up with a product. And I'll kind of go quickly here. Lessons learned, it's important to note that when you send an email, not everyone's going to interpret it the same way. We had to learn communication on a first-hand basis. It was extremely valuable for all of us to really realize what kind of losses are we going to get in tone, intent, interpretation, things like that. We had problems, but we overcame them. Follow the sun is great for preliminary design work for things that are happening in serial. It really accelerates that. When you get to parallel work, such as doing SolidWorks modeling, it's not as advantageous. However, in the manufacturing, it came back to be helpful in solving problems. International shipping, customs can be a pain. Do your work in the beginning so that it doesn't become a problem. And quickly, I'll hand back over to Coster to talk about the
lesson. As a conclusion, is an important issue for such a project. This was quite expensive, and we were fortunate to have Boeing behind us and eSpace sponsoring it. One of the lessons that we learned here that university cannot handle finances. So have universities, every university in your partnership should have their own budget. Okay. We had to find some other universities for doing some things, and that is a bad thing. Definitely take some time. Successes, the full design was done in a layout in 4 months. The aerodynamic analysis was done using the follow the sun principle. We have full control system was developed. The full delocalized manufacturing was very successful in 3 months. And everything stayed within mass and finance budgets that we had. We had some options as well, and in future we will continue on some of these issues of this concept. Basically, some results. So the FTS is a very wonderful thing. It has to be adapted to some specific projects. And I want to thank all these people that helped us. Mike Kiska is the program manager of the X48. He was on a conference call every week with students, which was fantastic. And even we had Bob Liebeck, who is the inventor of the X48 concept. He was part of this discussion. And we had many more people helping us with this project. And special thanks to our pilot that really flew this vehicle very nicely. Thank you very much.